Hello. Hello, everyone. I'm Andrija. I'm a cryptography researcher and geometry, and I'll be presenting a joint work with YJ. We worked on something called Semacalc. And first of all, when building privacy application on Ethereum, we always had this EVM trilemma. So you always had applications that you want to be cheap in smart contracts. You want to have a high privacy, which means that you use very efficient and audited hash functions and similar concepts. And you want to have a fast proving time for scaling. And it's kind of very hard to achieve all three. So first of all, you can do really easy smart contract cost with high privacy, but by using like SHA or catch-up functions. But the problem with that is your proving time of the circuit gets enormously huge, and everything gets very slow, and you cannot do that. If you try something else, if you try to use snark-friendly hash functions as Poseidon, MIMC, and I don't know how many you heard of, you get faster proving time, but now doing these hash functions, which are snark-friendly, are, so to say, not EVM-friendly, which means that it takes a lot of gas to update your smart contract with some, to just compute hash function in the contract. So it's very hard, as I said, to achieve all three, but what we are able to achieve with this protocol is to kind of actually pack and achieve all three, so that there is no more trilemma. Okay, so Semacalc, easy to say, is a very gas-efficient zero-knowledge set membership protocol. Okay, so maybe the key note is that if you compare current state of like Semaphore protocol or Tornado Cash, our protocol achieves like 90% cheaper insertions in the contract. Okay, so that's like the main point. The huge picture is that your proving time gets so low, around 50 milliseconds. Your verification cost also, since we have like a very customized protocol for making proofs and verifier, is in the cost almost similar as GROT16, which has the cheapest verifier to execute in the smart contract. We also added something called private information retrieval, which I'll speak later about. So this new kind of lookup arguments that are very popular last few years are always coming with some pre-computation part, and we cannot escape that. And that pre-computation part takes around 30 seconds, so to say. And after that, you can generate your proofs is like more than less than 50 milliseconds after this one-time pre-computation part. So it's currently kind of common to measure and benchmark your like proving time, verification cost, and in general gas cost of maintaining the group in size of 2 to the 20, and simply because if you want to get higher groups like 2 to the 30, it just gets so expensive and so slow. However, what we are able to achieve is this constant proof times, which enables us to go to extremely large groups, which for applications as like Zcash and Tornado Cash is very important, because you want to have that group maintained like forever. So what is the membership proof? It's very common primitive that is used in zero-knowledge applications. So simply have some public set of some commitments, and you want to prove that you own one or many of secrets which leads to commitments in those sets. And the most common approach now is doing it with Merkle tree. So you'll represent your group as a Merkle tree, and in order to prove that you know a secret to the Merkle tree, you will actually privately compute the Merkle path, and you'll just, the circuit, the proof, will just constrain that you're using the good root. Now, this is, again, a huge issue once you want to go to this 2 to the 30 groups, because your tree gets very deep. And let's say that you take the most friendly hash function today, which is like Poseidon. The smart contract cost of maintaining that tree is enormously huge. So it's like never used. However, we take very different approach. We built this very customized protocol based on MIMC hash, and we leverage KZG commitments. I don't know if you heard of them. So that's also a commitment scheme similar to Merkle tree, which gives some nicer properties as constant verification time. And now insertion in your group in the contract, instead of taking a lot of hashes through this tree, takes just a few elliptic curve operations in the contract, which gets to be just like 68K gas, which is extremely cheap compared to million or more for current state of the applications which use Merkle trees. It's general agnostic to curve. You can use any pairing-friendly curve. We built our system and bench it on BN254 just to be compatible with Ethereum. I'm not going to stay here for too long. The idea is that once you get to this Lagrange base setting and working with commitments in KZG scheme, you can leverage a lot of homomorphic operations from this commitment to very efficiently update your group, however large it is. So it's not that straightforward. Since you want an extremely huge group, you need to like store all Lagrange basis commitment in the contract, which again will be very expensive. So we again have to leverage some more efficient techniques to enable this, again, cheap updates. But in general, what we achieve is this 68K gas. It's very scalable. You can batch it very easy, and it's very easy to just maintain that group. Okay, so I don't know how interested you can be into this, but if you can like look at this formula where you update C, it's doing something that is called scalar addition and scalar multiplication and point addition, which happens to be, again, not that cheap in contract, but since you can update with just 2 of these, it's actually very, very cheap compared to what you do in hashing all your Merkle path. It's all done on chain, of course. Okay, so when we speak about these applications, you always want to have some kind of signaling or, so to say, whistleblowing or like just spending something. So all these applications are based on a few similar concepts where you have some public group, you have some secret, as we said, and only once you can spend something. So if you look at the Tornado cache, you put something in the pool, you prove that you have something in the pool, you withdraw, and then you cannot double spend again. So our goal was to really keep the same interface as all these applications, nothing to change on the API level to have like backwards compatibility and something that is very audited, so to say. So all changes that we made were only on the actual protocol level. So the interface itself is already compatible with all applications that are out there that are based on membership proofs signaling, which are preventing double spending or double signaling. Okay, so if you look lower, what's the difference from maybe the official version of Semaphore, which is the most popular primitive for this kind of proofs? As I said, we use different hash function, which is MIMC compared to Poseidon. And then we had to do a lot of math So you have something called calc plus, that's this new lookup argument, and we had to customize it in order to make it compatible with all that we want. But this is actually the key why we achieve this fast, like lower than 50 milliseconds prover time, that you can easily run in browser. Then I guess everybody is already familiar with Plonk. So the problem with Plonk is that your verifier in the on-chain can be much more expensive than GROT16, even though Plonk gives you some much better performance and much freedom when designing your protocol for the prover side. So we also had to do something similar to Plonk, but also like customized in order to achieve this very specific GROT16 verification target. And Halo 2, the framework developed by Zcash, also has the multi-open argument, which like allows you to prove that your polynomials are correct. And you also had to like build very custom protocol, which is kind of modification of this to again achieve all these things that we needed for the protocol. And now, as I said, you have to pre-compute a lot of data, and maybe that's also not very good for user and not easy to just put that burden on user. So let's just, again, high level see what's happening. So you have to, in about 20 seconds or more, pre-compute some data. Then you can many times generate the proofs in less than 50 milliseconds. You just submit proofs on chain, and that's it. Now, you can, as I said, do it on any elliptic curve. You have like a lot of freedom, but still you have to leverage all this data, do it all locally. Will you do it in browser? Where are you? How are you going to do setup? How are you going to update if group gets updated? That's kind of the problems that are not very specific to this scheme. These are the problems which occur in all these signaling-based privacy pools. So what we do, we privately outsource computation. So what I mean by saying that, there is something called private information retrieval, which allows you to download data from a public database where the server which holds the database learns nothing about which index or which data is being queried. Okay? So what actually you're going to do now, you're going to privately retrieve some data you need for proof, so that you don't need to bother by storing it, having maybe some secure extension and key management, in general, like some secret management platforms. So it's all pre-computed on one server. We did this with collaboration of this very nice team from Bliss, which are also working on private information retrieval. So what's happening on one server, that server actually maintains the group, and that server learns nothing about your privacy. It cannot do anything maliciously on you, so it's just like a helper. Imagine it as a relayer. And now what you can do, you can actually outsource all this pre-computation and efficient updates of the group to that specific server, or many of them, however, and then you privately retrieve the information you need to compute the proof, which is just like one query to some remote server, which is, again, very fast. It's all open source. You can see it on our GitHub. With all like benchmarks, with very detailed explanations and documentations, how this proving system work, how can you spin your own groups, how can you integrate it in already maintained applications, and how to migrate to this. And this thing for like private information retrieval is not necessary if you still have a system which does not leverage something like that. It's not must-have. That's just something that makes usage of these applications even easier. Here, we just put some code to show how easy it is to use. So literally you have a bucket where you can write data in that bucket, and you can just say private read, and you will read data from that bucket. Well, in our case, will be some quotients on G2 group of the elliptic curve, and I'm not going to bother you with that. But you just can take that, and the server who hosts database will learn nothing about which thing you queried. And if you think current applications can have that problem if you try to like time these queries. Like, it's common to have some servers maintain these huge Merkle trees from which you can take the Merkle paths in order not to store on your local storage and whatever. And now if you try to time attack, you can try to deduce which person downloaded which index and who is actually making the proofs. With this, it's just not possible. And now what we want to do next is also build a very tailored protocol for using Poseidon instead of MIMC hash function. In general, we just want to encourage teams to build tooling around this and migrate already existing applications into the space. We need to build something like WASM to give you the browser compatibility, but that's now all straightforward after this heavy lifting. And as I said, you can take this presentation, find all the documentation, all code, you can benchmark it locally, you can put your trusted setup into that if you already have something. Like, it's very easy to just migrate and start using this. Also, Vijay made a very nice documentation where you can really step-by-step see how everything of this works. And yeah, thank you. I guess I should stay here for questions.
Has a question, feel free to raise your hand.
Yeah.
Yes. Do we have volunteers in the room to pass the mic?
Hello, thank you for a nice presentation. What is the good use case for this?
Okay, so this is like just a low-level protocol for this kind of membership proofs. But if you look now, all kind of private voting that happens on Ethereum is based on this. All these privacy applications for as Tornado Cash, Zcash, they're all built on this concept. So this is just like a new kind of protocol which just optimizes kind of all parts of those protocols. So use cases already there. This is not like building a new application. This is just speeding up all those applications.
Is there a chance that this could be used in a way for authentication and authorization? Like, could this replace current login
Yeah. I think that's already being used on a lot of these on-chain governance kind of things, where you literally prove that you have credentials that are in the group. So yeah, that's quite a common thing to do.
Thank you.
Yeah, there is.
Do we have another question? We do.
Hey, so you mentioned there's something akin to private key. So I want to understand, like, having the private key and having this something akin to private key. How does that relate to user experience?
Yeah. Okay. So when I say private key, it can mean a lot of things. So here you have like a few values that are your witness, which you can call private key, and now you need to keep them somewhere secure. Yeah. And also, since these groups can, over the time, they get larger, like you have new stuff inserted, some stuff spended, and they're changing. You wanna always have as big group as possible when making the proof, because that gives you the biggest privacy, so to say. So you kind of want to keep up to date with how these groups is getting larger. And now you need to have, like, as in a Merkle tree-based proofs, you have a new Merkle tree commitment. Now you need a different Merkle pet to prove that you are the membership. To prove that you just have a valid Merkle pet leading to the commitment. Here, however, since we have this different kind of commitment, you have some elliptic curve points that you need to preserve and pre-compute. So yeah, we literally just enabled user not to care about it, and they can just retrieve it privately from this server that actually does all of that. And that server cannot do anything maliciously, like if they do something wrong, you can just slash them, and they can never learn anything about your actual private key.
Nice, nice. So one more question, if I may, do you have time?
Please, go ahead.
So you mentioned private voting as one use case. So maybe a noob question, how would you tally the votes in that case?
How would you do what?
Tally, compute the votes.
So what's actually happening is the signal you're sending. It can be like a message, a memo, or like a vote. It's public. The application just allows that nobody learns who from the group actually sent that vote. So your smart contract will just count the vote, and that's it.
So it's privacy preserving, right?
Yeah.
Thank you.
Do we have any more questions? Yes, there's a hand there.
Okay, yeah.
Sorry, this 20 seconds of pre-compute, that's using CPU, GPU, or something else?
It's just simple CPU precomputation, but you have to do it in order to have this calc plus lookup argument, which I'm just not gonna go there now, but it's based on just like starting with some group, pre-computing something, and then we again add some more stuff to that to enable also very like fast updates of that group. So yeah, but you kind of do it just once.
All right, thank you very much.
Any more questions from the audience? Raise your hand if you do.
Yeah, I think that's it.
Do we have any more questions? Okay then. So please give it up for Andrija for an amazing talk.